Okay, next up we have Tianqi Zhu, software engineer at Stripe, presenting on feature generation in real-time and batch without time travel. Tianqi is one of the tech leads on ML infra team at Stripe. The team builds out the platforms to power Stripe's fraud detection systems and other ML products. Prior to that, he worked on the Sigma team at Stripe and search infra team at LinkedIn. Tianqi has spent the last 6 years on big data and large real-time systems. He graduated from UPenn with a master's degree in electrical engineering. Please welcome Tianqi.
Thanks everyone for coming. I'm Tianqi from Stripe. So today I'm going to talk about Semblance, which is a feature generation framework for real-time and batch. So 2 years ago, before Semblance, our users were complaining about how long it took to launch a model to production. It can take anywhere from 6 months to a year to do that, and most of the time are spent building real-time features for the model in production. And even that our users can have a model in production, very often they found the features are different in production than the features they use for training. As a result, model performance was much worse than expected. Now, fast forward 2 years. We did an interview with one of our users a few days ago, and he was saying that it only took him 4 weeks end-to-end to prepare raw data, write Semblance feature code, and generate features offline, doing data validation, model training, model evaluation, and also backfill the feature and deploy the feature with the model to production. Also within that 4 weeks, he split some time to do other things. So it's at least 12x speed up for ML velocity in this case, and not to mention the improvement we have made for more consistent features for online and offline. So what's the magic? Well, before we design Semblance, we dig into a few common problems that our users were facing. One of them is time travel. And I know that some of the people are attracted by time travel, but I don't know how to time travel, so I guess I better put a fancy picture here. And time travel in machine learning means that you are using future information as features to train your model. Very likely, the future information would contain strong signals related to the labels, or even containing the labels themselves. As a result, when you have the model offline, the model performance is really good. But once you deploy the model to production, because the future information is not there, the model performance degraded dramatically. Another problem that our users were facing at that time is mismatched features for training and scoring. There are a lot of reasons that this could be the case, and time travel could be one of the reasons. Other reasons including different implementations for generating features offline and online. For example, it's often that people will have Python code to generate features for training, and then they will build the real-time features for scoring in other languages such as Python or such as Java or Scala. And in those cases, you may have different implementations and even containing bugs to produce different features. Another common case is that people will use impractical features for training. For example, if a feature takes 30 seconds to generate in real time, you may still be able to use those features for training. However, if in scoring time you have a low latency environment, then the feature will always be missing at scoring time. Last but not least, another challenge that our users were facing is to obtain correct historical view of the features at the time they were used for scoring. So before Semblance, a lot of our users are using multiple databases to generate features in real time. So it's really difficult to figure out what's the value of a feature at the scoring time, say 3 months ago. Someone may argue that it's possible that you can log the features in scoring time and replay it later. However, if a user wants to use a new feature and backtest it, she needs to be really creative about how to generate the backfill data for that. So to solve these problems, Semblance borrowed some concepts from functional reactive programming. There are two basic concepts in FRP. One is events, which are values that occur at a discrete moment in time. And the other one is behaviors, which are values that vary over time. One major advantage of FRP is its implicit treatment of time, which means that the value of a behavior can only be determined in terms of time t, or events aggregated up to time t, or values of other behaviors at time t. So it's impossible to peek into the future. Here is a graph of how the discrete FRP model works. There are events that coming in at different time points, and you still have values at any given moment. But the value for a behavior is like a step function that only changes when the event comes into the system. And similarly, we will have events and features in Semblance as the two key concepts. The event is similar to the event in FRP, which are events coming from one or multiple streams. And the feature stands for a state about something at any given moment. And the key could be anything meaningful in certain scenarios, be it merchant ID, customer ID, car number, IP address, etc. And I will come to how we can generate features and why feature can have a value at any given moment shortly. Now let's focus on the events first. In Semblance, we offer a few functions to convert events. We have a map function that can convert an event of A to an event of B. We have concat map, which is similar to map, that can convert event of A to event of B, given a function that converts A to an iteratable of B. We also have filter functions that can filter out events using a predicate. Last, we also have a concat function that can combine two events of A into one event of A. This could be extremely useful because if you think about the type of the event A, it could be either of X and Y, which means that we can have an event of left X with an event of right Y and combine them into a final event of either X and Y. And if you think about the X and the Y can be another either of two ethers and so on, eventually you can have you can join an arbitrary number of streams of different types into one stream. And that's basically how we do lookups or the joins. And I will come to that later. So once we have the events, we can call feature.latest or feature.sum on events to generate a feature. And we can also zip multiple features into one feature of, say, K of V1 and V2. And someone may notice that the value type of the feature.latest is different from feature.sum. And this is not a typo. We use option of V as the type of latest feature because it's possible that at the time we want to get a value for that feature, we have never seen an event for that certain key. So in that case, we will return none. While in the sum case, we require users to provide a combiner that will provide an empty value or default value for V so that we know when we don't see an event for this key, what's the value to be returned. And by the way, you may find that a lot of the terminologies are from Scala because Semblance is built on top of Scala entirely. So in addition to the empty value of V, we also require combiners to tell us how to combine two Vs into one V so that we know how to sum the stream of events into a single value. And here is a code example of how we generate Semblance features and events. At the top, we will generate a source event. And behind the scene, we have code to handle things like how to read offline and online data source, how to deserialize and serialize the data, how to extract time information from the events. But I'm not going to expand on that here. Once we have the source event, we can convert the event into events that we are interested in. For example, we can create an event of amount by merchant or merchant cart pair. And once we have those events, we can call feature.sum or feature.latest on those events to create features we are interested in. And at the bottom, we can zip features together to generate the feature vector that we would like to use to train our models. And here is an example of how we can process an event based on the feature DAG we have in the previous slide. So if we have a merchant 1, $99, and cart 1 as an event, then we will have merchant 1, 99 as an amount by merchant event, and through the sum operator, we will have a feature. And let's assume that the value before applying the event is $99 for merchant 1, then summing the new event, we get $198 for merchant 1. And similarly on the right, through the latest operator, we got the cart 1 for merchant 1 as the most recent cart by merchant feature. And we can zip two features together at the end to get a row that we will be using for training, which is $198 and cart 1 for merchant 1. Now, we have gone through the basic operators we have in Semblance, but people also like to join data from different tables. And Semblance support joins through lookup. An event can look up into features as long as you provide a function to convert the event to a key in the feature. The table below explains how this works. Say at the initial time, we have a feature of kv0. And at time t1, when an event a1 comes in, we'll get a lookup result as a1 and v0. And then when a2 comes in, we'll get a2 v0. If, say, feature value was updated at time 3 to v3, then any event comes in after that will get a lookup result as a4 v3. Now note that the timestamps here are invisible to the users. They cannot say that, give me the value for a feature at certain time. What they can do is provide us with an event, and we know how to extract the time from the event, and also figure out what's the value for a certain feature at that timestamp. So this is a built-in mechanism to avoid time travel and minimize the chance that users will make such an error. And also note that the return type of the lookup is also an event, which means that you can use this event to look into other features, which we call nested lookups. So this is a powerful tool to join multiple tables, but I will come to why we should avoid doing that as much as possible later. In addition to the lookup function, we also have utility functions like lookup before, lookup after, lookup if defined, etc. And the major difference between lookup and lookup before is that sometimes an event may look up into a feature that will be updated by the same event. In this case, if we are using lookup, we will get the value of the feature after applying the event. But lookup before will give us the value of the feature before applying the event. So for example, if we have kv0 at the initial time as a feature, and if event a1 comes in and will update the feature value to v1, with lookup before, we can get the lookup result as a1 v0. Well, in the lookup case, we'll get a1 v1 as a lookup result. So here is a system view of how we run the Semblance system in production. We have the real-time layer that consumes events from Kafka and transform the events, aggregate them, and put the feature values in an online data store. We also have a batch layer that run batch jobs every day to read data from S3 and generate feature values offline. We put them into an offline data store. Both the online and offline data store is partitioned by batch, so that the more batches we have in offline data store, we will shrink the window of batches we will use in online system to fix the accumulated errors that we may have in the online batch. We also have a service layer that receives HTTP requests from users, get features from online and offline data store and combine them and return to the users as a feature to be used in real time. So a lot of companies in Silicon Valley provide free lunch, and people like free lunch. So we provide free lunch in Semblance. For example, the event and features are purely business logics. When users are using Semblance to define the events and features, they don't have to think about what are the underlying technologies they will be using. For example, they don't need to worry about what are the storage systems they are going to use, what are the streaming system or the batch processing system they are going to use. Instead, we develop the interpreters and compilers to compile the events and features into different environments. The first interpreter we have is an in-memory interpreter for testing purpose. And then we build a Hummingbird compiler that can compile features into offline Scalding jobs. And then we build a Storm compiler to compute features in real time. However, the Storm compiler is too slow. So we build our own real-time compiler from scratch and reduce the latency to around 500 milliseconds initially. In addition, we also build a Spark compiler to allow people to generate features in Spark. So the benefit of decoupling the business logics and the backends is that people don't need to write a single line of code to use the new compilers that we have built. They can also enjoy the improvements that we made to these compilers without doing anything. And in late 2018, we decided to work on Semblance v2 to improve the lookup efficiency. As a result, we built a new Scalding compiler, a Scalding on Spark compiler, and a real-time compiler v2 to replace the existing compilers. As for performance, after we launched Semblance v2, the match rate for features in training and production was increased to 98% from 85%. And by match rate, I mean we check all the columns in the feature vectors in training and production. As long as there is one column that is different, we call that a mismatch. And as a result, the model performance was boosted by 35%. Here is a table of some of the features that we are running in production. So for the most complicated and largest feature we have right now, it uses about 90 terabytes of data in online and offline data store with a key space of 22 billion different keys. We are consuming about 10,000 events per second and doing around 1.2 million read and writes to the online data store. With such a system load, we managed to keep the P50 latency under 30 milliseconds and P99 under 200 milliseconds. And for the future work, one thing that we have regretted is that we didn't put a limit on how complicated the features can be. So some of our users have abused the system to create really complicated features. So on the left, the purple circle is the final feature that they will be using in real time and offline. And on the right, there are a bunch of green circles that represent the source events. And in the middle, there is a huge pile of red circles of intermediate features that will be looked up or zipped into the final feature. Anyone wants to guess how many intermediate features we have in this graph? 150? 30? It's in between. We have 89 intermediate features here. So it puts a lot of pressure and latency to the online and offline systems we have. Other things, including we want to build a feature store to share features built by different teams, and also to support range and sliding window. Currently, Semblance supports sliding window through a list because we can use list as a type of the feature value. However, implementing such a sliding window could be quite tricky, and we want to make it easier for the users. Like any big projects, Semblance was built by a group of very talented engineers, and I'm lucky to work with them on such an amazing project. This is all I have, and thank you for your time.